Here is a demo platform including a DUT, a PV simulator, a grid simulator and an oscilloscope. I am going to show you how to use the grid simulator and the PV simulator to achieve anti-landing tests by this demo platform. On the left, it is the DUT, a grid-connected PV inverter. Its DC input range is 270V950 VDC, the maximum AC output apparent power is 16.5 kVA, and the maximum AC output current is 24A. The white unit on the bottom right is the IT7900C, which can be used as a PV simulator here. It has a built-in PV simulation mode, by which you can edit the PV curve through the 4-point method of VMP, PMP, IC, and VOC. The black unit in the middle is the IT7900 grid simulator. It can simulate voltage disturbance, three-phase unbalance, phase loss, frequency change and so on. First, we import the PV curves into the DUT, enter the SAS mode through the menu. Then let us configure the curves through the 4-point method. Here we set VMP as 700V, imp equals 10A, which is equivalent to the MPPT, about 7 kilowatts. Then we set VOC as 800V, IC as 15A. OK, now turn on the PV simulator to provide DCI, MUP for the inverter. Next, we set the IT7900 power grid simulator to 220V, 50 Hz and select 3-phase output. Start the output of the grid simulator, provide a voltage signal to the AC terminal of the PV inverter, then start the inverter. Now, you can see two sets of curves on the oscilloscope. The blue waveform represents the voltage at both ends of the inverter, the purple waveform is the output current of the inverter. Because the inverter is still in the startup phase, there is no current feedback into the grid simulator for the time being. Therefore, there is no change of the purple curve, and it is showing a current of 0A on the IT7900 grid simulator. Now the inverter has started working, so the feedback current is gradually increasing. On the oscilloscope, you can see that the amplitude of the purple waveform is gradually increasing. The power generation is about 639 kilowatts. Now, the current and power generated by the inverter are basically stable. We can see that there is an icon called RC in the lower left corner of the main menu on the IT7900. It represents the I-landing test mode. Let's click to enter the interface. In the VAL display area, the lower left corner of the screen, we can see that the current generation power of each phase of the inverter is approximately 2 for 5 kW. The RC function of IT7900 provides two modes. One is RC mode. You can directly set the resistance, inductance and capacitive reactance of each phase. The other is PQ mode. You can set active power, capacitive reactive power, and inductive reactive power. Moreover, users can set THE active power and reactive power of each phase independently. Now let's configure it. We set the active POW equal to the capacitive reactive power and equal to the inductive reactive power, both of which are set to 245 kilowatts. After setting phase A, switch to phase B, do the same setting. Of course, you can also configure it through RLC mode. Now we have finished configuration of all the 3 phases. At this time, we need to close the K2 switch in the interface. The built-in island topology diagram of IT7900 grid simulator is in full compliance with the requirements of grid-connected laws and regulations. The islanding test regulation standard is IEC62116. As required, now we click Close to close the K2 switch. Now, all the power generated by the inverter is consumed by the RLC load. Next, in accordance with the test requirements of the islanding regulations, the K1 switch needs to be closed so that the PV inverter enters the islanding state. Let's check the oscilloscope. The first channel is to monitor the K1 switch. When K1 is disconnected, the I6 pin on the IT7900 rear panel will output a pulse signal, and there will be a Y/LO curve displayed in channel 1. We can see it later. The islanding test also has a time measurement function, which can automatically measure the islanding protection time. According to regulations, the islanding protection time refers to the time from when the K1 switch is disconnected to when the feedback current is less than 1% of the output current. When the K1 switch is off, the equipment will output a pulse signal and start timing. We can also set the cutoff condition of the timer when we enter the sub-menu. Here we set the current as the cutoff condition. The feedback current is about 11A. 1% of it is 011A. So let's set the timing cutoff current as 011A. Okay, the setup is complete. Let us close the K1 switch and press Open on the panel. The island protection time displayed is 332 ms. Let's take a look at the waveform captured by the oscilloscope. Now the oscilloscope shows that the yellow waveform of the first channel is the K1 signal. When K1 is disconnected, I6 on the rear panel of the grid simulator will output a pulse signal, which is the starting time of the island protection. Let's adjust the waveform. Well, the actual measurement time of the oscilloscope is about 29 ms. Because IT7900 grid simulator samples multiple cycles, when sampling current, there will be a measurement delay. Therefore, we see that it shows the test time is 332 ms, which is a little more than the oscilloscope measurement. But the landing protection time required by regulations is not more than 2 seconds, so the time difference of just some milliseconds here is acceptable. That's all for today's demonstration.